Have you ever stopped to think about what connects the pencil you use to write, the sugar that sweetens your food, and even the fuel that powers cars and buses? It might sound like a riddle, but the answer is a single, incredible element: carbon. That's right. Carbon is everywhere, and I mean everywhere. It's in the air we breathe out as carbon dioxide. It is the backbone of the molecules that make up you, me, and every living thing on this planet. From the simple graphite in your pencil lead to the complex chains in the plastics we use daily, carbon is the silent, unsung hero of our material world. It's the ultimate building block, creating an amazing variety of substances all around us. So, what is this master builder, really? In the world of chemistry, we give carbon a simple symbol: C. On the periodic table, it holds the spot for atomic number 6. This number is super important. It tells us that a carbon atom has 6 protons in its nucleus, and when it's neutral, 6 electrons orbiting that nucleus. Think of it like a tiny solar system. The electrons are arranged in shells or energy levels. For carbon, 2 electrons are in the first, innermost shell, and the other 4 are in the outer shell. This outer shell is called the valence shell, and these 4 valence electrons are the key to everything that makes carbon so special and versatile. Now, let's talk about those 4 outer electrons. In the world of atoms, having a full outer shell is the ultimate goal. It's like winning a gold medal. Most atoms want to have 8 electrons in their outer shell to be stable. Carbon is in a bit of a tricky spot. It could try to give away its 4 electrons, but that takes a lot of energy. It could also try to grab 4 more electrons from another atom, but that's also a tough job. So, what does a clever atom like carbon do? It decides to share. Instead of giving or taking, carbon forms partnerships with other atoms by sharing its electrons. This sharing creates a very strong and stable connection. This special type of connection is called a covalent bond. Imagine you and 3 friends all want to build something amazing with Legos, but none of you have enough bricks on your own. If you all put your bricks together and share them, you can build incredible structures you couldn't make alone. That's exactly what carbon does. By sharing its 4 valence electrons with other atoms, it can form 4 strong covalent bonds. This ability to form 4 stable bonds is what allows carbon to create long chains, intricate rings, and complex 3-dimensional structures, which is the very foundation of the vast and wonderful world of organic chemistry. Now, here's where things get really cool. Imagine you have a huge box of identical Lego bricks. Using those same bricks, you could build a tall tower, a long bridge, or a hollow sphere. The bricks are the same, but the way you arrange them creates completely different structures with different properties. The chemical world has a similar phenomenon, and we call it allotropy. Allotropy is the ability of a chemical element to exist in 2 or more different forms, in the same physical state. These different forms are called allotropes. For carbon, this means that pure carbon atoms can bond together in different ways to create substances that look and behave completely differently. Think of it like carbon is an actor who can play wildly different roles. In one role, it's the toughest substance known to humankind. In another, it's a soft, slippery material that we use to write with. And in yet another, it's a molecule shaped like a tiny soccer ball. These are all made of nothing but carbon atoms. The only difference is the geometric arrangement of those atoms and the bonds between them. This structural variation is what gives each allotrope its unique set of properties, such as hardness, color, and electrical conductivity. It's a powerful demonstration of how important structure is in chemistry. The 3 main allotropes of carbon that we are going to explore are diamond, graphite, and fullerene. Each one is a testament to carbon's amazing versatility. Diamond is a brilliant, transparent crystal. Graphite is a dark, opaque, and soft solid. Fullerene is a molecule made of carbon atoms arranged in a sphere or tube. It's mind-blowing to consider that the same element is responsible for such a diverse cast of characters. By understanding how the carbon atoms are connected in each case, we can unlock the secrets behind their distinct properties and find incredible uses for them in science and technology. Let's get ready to meet these carbon superstars one by one. we'll see how a simple change in the bonding pattern transforms the humble carbon atom into materials with extraordinary abilities. From jewelry to industrial cutting tools, from pencil lead to lubricants, and even into the realm of nanotechnology, carbon's allotropes are all around us, playing crucial roles in our lives. It's a fantastic journey into how atomic architecture shapes the world we can see and touch, all starting with the arrangement of those 6-proton, 6-electron atoms. It's science, and it's awesome. First up is diamond, the undisputed champion of hardness. What gives diamond its incredible strength? It's all in the bonding. In a diamond crystal, every single carbon atom is covalently bonded to 4 other carbon atoms. This creates a rigid and strong 3-dimensional network. Imagine an endless, perfectly interconnected jungle gym where every joint is superglued to 4 others. This structure, called a tetrahedral lattice, extends throughout the entire crystal. There are no weak spots. To scratch or break a diamond, you would have to break countless strong covalent bonds simultaneously, which requires a massive amount of energy. That's why diamond is the hardest natural substance on Earth. This rigid structure also explains another key property of diamond: it's a terrible electrical conductor. For electricity to flow, there need to be mobile electrons that are free to move through the material. In diamond, all 4 of carbon's valence electrons are locked into strong covalent bonds between atoms. They are not free to wander around. They have a job to do, and that job is holding the crystal together. With no free electrons to carry an electrical current, diamond acts as an electrical insulator. Its brilliance and hardness make it prized for jewelry, but its incredible strength also makes it essential for industrial applications like cutting, grinding, and drilling. Now let's meet diamond's alter ego, graphite. If diamond is a rigid 3-dimensional jungle gym, graphite is like a stack of paper. In graphite, each carbon atom is bonded to only 3 other carbon atoms, forming flat, hexagonal rings, much like a honeycomb pattern. These rings join together to create vast, 2-dimensional sheets or layers. The bonds within these layers are very strong covalent bonds, just like in diamond. However, the forces holding the different layers together are very weak. These weak forces, known as van der Waals forces, allow the layers to easily slide past one another. This is what makes graphite feel soft and slippery. This unique layered structure explains why graphite works in your pencil. When you write, you are essentially scraping off layers of graphite onto the paper. It also explains why graphite is a good electrical conductor, unlike diamond. Since each carbon atom is only bonded to 3 others, 1 valence electron per atom is left over. This delocalized electron is not locked in a bond and is free to move along the layer. This sea of mobile electrons allows graphite to conduct electricity, making it useful for things like electrodes in batteries and electric motors. So, the same element, carbon, gives us both a perfect insulator and a useful conductor just by changing its bonding arrangement. Our journey through carbon's allotropes doesn't end with diamond and graphite. In 1985, scientists discovered a whole new family of carbon structures, the fullerenes. The first one to be identified, Buckminster fullerene, or C60, is a beautiful molecule with a truly iconic shape. It consists of 60 carbon atoms arranged in a hollow sphere resembling a soccer ball. This structure is made up of interconnected hexagonal and pentagonal rings of carbon atoms. It's named after the architect Buckminster Fuller, who designed geodesic domes with a similar pattern. This discovery was so important, it earned its discoverers the Nobel Prize in Chemistry. Unlike diamond and graphite, which are giant network structures, fullerenes are distinct molecules. You can have a C60 molecule, a C70 molecule, and so on. They are like tiny, hollow cages of carbon. This opened up a whole new field of chemistry and nanotechnology. Scientists realized they could trap other atoms or small molecules inside these fullerene cages, potentially for applications like delivering drugs to specific parts of the body. Since their discovery, other related structures have been found, including long, hollow tubes known as carbon nanotubes, which are incredibly strong and have unique electrical properties. promising revolutionary advances in electronics and materials science. So, let's recap what makes carbon so incredibly special. We've seen that its ability to form 4 strong covalent bonds is the first part of its secret. This allows it to create the stable backbones of millions of different compounds. The second part of its secret is allotropy. By arranging itself in different ways, it can produce materials with a stunning range of properties, from the hardest substance known, diamond, to a soft lubricant, graphite, and even to molecular soccer balls, fullerenes. Carbon is truly the king of versatility in the periodic table, all thanks to its unique bonding capabilities and structural diversity. And believe it or not, we've only just scratched the surface of carbon's amazing abilities. We've focused on covalent bonding and allotropy, but there are 2 other massive concepts we need to explore to fully appreciate this element. In our next discussion, we will dive into carbon's tetravalency, its consistent ability to form 4 bonds, and its incredible power of catenation. Catenation is the ability of an element to form long chains and rings by bonding to itself. It is this property, combined with tetravalency, that allows carbon to form the millions of organic compounds that are the basis of life itself. So get ready, because the carbon story is about to get even bigger.